Okay, welcome back. So today I'm going to talk about trusses. What is a trusses? Well, the trusses can be used in so many types, such as the roof. As you can see here, the roof or the bridge. You can go to Google for the bridge trusses. And there's so many types of bridge trusses, like Brad or Warren or Cages, Think, or sometimes can you ask the dome trusses, or tower, or crane. So trusses can be used in many types of structure. So how does it work? So the member of the trusses only can resist the axial force, which is the force go along the member, go inside the member. It cannot resist the perpendicular force like this, like the beam, a normal beam. I give you an example. So if you are going to study the subject called static at Charles Darwin University, you're gonna have a project called pasta trusses. So that's a member. It is very easy to be break because it cannot resist the perpendicular force like this. So the members only can resist the compressive force or the tensile force. Okay, I would like to show you my design on the static subject. So as you can see here, all the thick member is under the compression, and all the thin member, such as the member under the bottom coat, is under tensile. So it's very thin. You don't need the thick member at the bottom coat because it's under tensile. So it's broken. So this one resisted 8.5 kg of water, and it only weighs 300 grams of pasta. That's a bucket of water, 8.5 kilograms. And my second design is for the thicker pasta, and because this bucket is 10 kilograms of water, so I put a rock in, make it a bit heavier. In this time, it was 12 kilograms of water in here, but it broke at the 13.2 kilograms of water. It's broken. Okay, that's how the trusses work. So just keep in mind, the member in the trusses only can resist the axial force on it, not the perpendicular force like this. Right? That's how trusses work. So trusses is a structure, so it has determinate structure or indeterminate structure, unstable structure or stable structure. So for example, if you have the trusses, so in here you have a roller support, and in here you have the hinge support. So the trusses can be called at the determinate trusses when the number of member plus to the member of reaction equal to 2 times of the joint. So M plus R equal to 2 joint DJ, right? That determinate. If it's greater than 2 joint, it's indeterminate. If it's smaller, it's definitely unstable. But in this case, before, we cannot say it is stable or not. We need to analyze it to see if the structure is stable or not. So it can be determinate trusses but unstable, or it can be indeterminate trusses unstable. So what is M? M is the number of member. So how many member here we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and then 13. 13 of member. So what is R? R is the number of reaction in here. So in here we have 1 because of roller support, and at the hinge support we have 2. So in total we have 3. And then how many joint? 1 here, 2, 3, 4, 5, 6, 7, 8 joint. Joint equal to 8. So now 2 joint equal to 16. In here M plus R equals 16. So in this case, so we have the determinate structure. But is it stable or not? It is stable. That's just a rule of thumb because it can move. If you force in here or whatever, it won't move. It is stable. But for example, if you put more roller support, so in this case, M equal to 13, right? But R equal to 1, 2, 3, 4, 5. So M plus R now is 18. 2 join equal to 16. So now M plus R greater than 2 join now. So it can be said that this Trusses is indeterminate. But is it stable or not? It is unstable now. Because look, if you have the force in here, the whole structure will move this way to the right. So that's how you analyze it. I'll give you another example. So for example, you have this structure, you have a ruler, and the hinge here. Right. So the M now, M equal to 1, 2, 3, 4, 5, 6, 7, and 8. M equal to 8 now. What is the reaction? Reaction is 3 because 1 here and 2 here. Right. So what is 2 join? 2 join is equal to 2 multiplied by 1, 2, 3, 4, 5, 6. So that's 12. And this one, M plus R equal 12 too. So M plus R equal 2 join. So it can be said that the structure is determinate. But is it stable or not? No, it's not stable. Look. So if you force in here, the structural can move this way. It will collapse something like this. So it's unstable now, right? Okay, that's how you determine the structural is determinate or indeterminate, stable or unstable. Okay, now we are going to solve for a determinate Trusses. So for example, if you have the Trusses like this, so first thing we need to do is a free body diagram. So it's very simple because in here we have the roller support, which means we will have the vertical reaction V1. Let's call it V1. In here we have vertical reaction at the node 7, so V7, and in here we have the horizontal reaction, which means let's call it H7. Okay, that's our free body diagram. So we have 4 meter and 4 meter here. So as you know, we have the angle load in here. We can rearrange it to the vertical load and the horizontal load. That's the vertical and that is the horizontal. So what is the value of the vertical load in here? It's going to be 15 multiplied by cos of 45, which means 10.6 kilonewton. And this one is 10.6 as well because it's same thing, 45. But just keep in mind, sometimes the angle is not 45, it can be 30 or something like that. You need to consider it. And so now first thing we need to do is to calculate the vertical reaction at node 1 and node 7. To calculate the vertical reaction at node 7, we can take the moment at point 1 equals 0. So sigma m1 equals 0, right? So what we have here is 5 kilonewton. The 5 kilonewton make the member rotate clockwise, which means it's positive 5 multiplied by the lever arm, which means 4 meter. Right. The vertical reaction here also make the member rotate clockwise. See, it's clockwise. So plus 10.6 multiplied by the lever arm. The lever arm now is 8 meter. 8 meter. Now the horizontal load in here now make the member rotate anti-clockwise. It's anti-clockwise. So we have the negative sign. 10.6 multiplied by the lever arm, which means the distance from the load to the support, which means 4. Okay, what else do we have? We have the V7. The V7 now it makes the member rotate anti-clockwise. So we have negative V7 multiply by the lever arm, which is mean 12, and then it's equal 0. But I will just change this here. So what will be the value? So the V7 equal to 5.2 kilonewton. V7, 5.2 kilonewton, right? Okay. Now to calculate the V1, you can either take the moment at point 7 equals 0, or you can take the sigma Fy equals 0. So V1 plus 5.2, which is a vertical direction at 7. And then what else do we have? We have minus, because it goes downward, minus 10.6. What else? Nothing else, right? So equals 0. So from here you will have V1 equal to 5.4 kilonewton. Now to calculate the horizontal reaction at point 7, you can use a sigma Fx equals 0 because it's going to the right, so I call it positive sign. So you have positive 5, and then you have minus 10.6, and then last one is the H7, right, equals 0. So the H7 equal to 5.6 kilonewton. Now I'm going to use the joint method to solve for the force in each member. So we need to start at the node 2 first. Look at node 2, I can say that there's a load go like this with the value of 5 kilonewton. I can say it straight away, or you can assume that the member here is under compression, and you write the equilibrium condition like 5 here, and then you minus to the F24 equals 0. So you will have the F24 equal to 5, of course it's compression. So in here we don't have any vertical load, so of course the F12 equals 0. Can be clearly seen that. So by analyzing only the node 2, you can find the force in two member, which is the member 2,4 and member 1,2, right? The next one I'm going to do is node 1. So I'm assuming that the member 1,4 is under compression, right? So that's the sign convention. If it go out of the way, it is under tension. So that's because the member here is 4 meter, and this one here is 4 meter as well. So the angle here will be 45 degrees. Our equilibrium condition will be positive 5.4 because it's going up, and then minus to the F14 multiplied by the cos of 45 degree equals 0. Right, so from here you will have F14 equal to 7.64 kilonewton. Yeah, so 614 here is compression. Okay. So now I'm going to write a equilibrium condition for the F13. I am assuming that the member 13 is under tension, so it goes this way. So I going to have what? F13 plus F13 minus to the 7.64 multiplied by cos of 45 degree equals 0, and then you're going to have the F13 equal to 5.4. Okay, now what else should we do next? So we cannot do the member 3 because we only have one equation here, but we have 1, 2, 3 unknown. 1, 2, 3 unknown. So we need to analyze the node 4, which we have 2 equations and 2 unknown. Easy peasy. So number 4. 1, 3, 6, 5. So should I find the force in the member 4, 6 first or in the member 3, 4 first? It really doesn't matter. So let's do the number 4, 6 first. I assume that the member 4, 6 is under compression. So what will be the value? 5 plus 7.64 multiplied by the cos of 45. Then minus to the F46 equals 0, right? So the F46 equal to 10.4 kilonewton. 10.4 kilonewton, right? The next one is F34. So with the F34, I will assume it is under tension now. Minus F34 plus 7.64 multiplied by the cos of 45 equals 0. So we have F34 equal to 5.4 kilonewton. The next one I'm going to do is a note 3 because we have now 2 equations and 2 unknown, right? So let's do the note 3. 3, 4, 26, 25, 21. Okay, on this one, can we do the force in the member 3, 5 first? The answer is no, because we have 3, 6 is unknown, so we cannot calculate the 3, 5. So we need to calculate the 3, 6 first. Okay, let's do it. So I will assume the F36 is under compression now. So 5.4 minus to the F36 multiplied by the cos of 45 equals 0, right? So we have F36 equal to 7.64 kilonewton. Now I can do the force on the member 3, 5 because I have the force on the member 3, 6 that we have just calculated. So again, I will assume that the member 3, 5 is under tension. So minus 5.4, right? Minus to the 7.64 multiplied by cos of 45. What else? Nothing else. So plus to the F35 equals 0, right? So in here F35 equal to 10.8 kilonewton. Here is 10.8. This one here is 7.64. Okay, what next? So next one I'm going to do is number 5. 5. Okay, so it can be clearly seen that the force in the member 5, 6 is 0 because we don't have anything in here. We don't have any external load in here, so it's going to be 0. And this side, it can be clearly seen that again the force on the member 5, 7 will equal to the force on member 3, 5, and it is under tension. So 10.8. It was an easy one, is it? So now which one do you want to do? I will do the number 8. 8. 7. 96. So because we don't have any external load in here, the force on the member 6, 8 and the force in the member 7, 8 will be equal to 0. So 0 here and up 0 here as well. So basically they waste the material here. They waste because it didn't carry any load. Now what should we do next? I'm going to do the note 7 because that's the easiest way to do it, because we only have the member 6, 7 need to be solved. Everything is solved now, so I'm going to use the note 7 to solve for the member 6, 7, or I can use the note 6 to solve it as well. You can either use the vertical case or you can use the horizontal case. So I will assume that the member 6, 7 is under compression. So I use the vertical first, which means 2.5 minus to f67 multiplied by the cos of 45 degree equals 0, and in here you will have the f67 equal to 7.35 kilonewton. You can use a horizontal one, which is f67 multiplied by cos of 45 minus to the 10.8. I forgot the horizontal reaction in here, which is 5.6. So I have 5.6. What else? Nothing else, right? So now f67 equal to 7.35. So it's correct. That's how you solve all the force on the member. That is the joint method. It takes a bit of time to do it. Okay. On the next video, I will solve this one using the cut method, which means they will cut between the member, in the middle of the member, something in here, and in here to solve the force on the member. Alright? Okay, I see you on the next video. Thank you.